okay, what did we do last time? Because we'll need that. What we did is that we solved an eigenvalue problem. But we said that, okay, suppose we take a spin half particle. So we are taking a spin half particle, and we have the particle, suppose in its, we take some basis, which is the eigenbasis of the SZ operator. Okay, so the eigenbasis, we said plus for the state one, half. We are writing it as plus, but because this is going to be the eigen state of the SZ operator or S3 operator, I'm going to put a small z here. And similarly, the half minus half, the down state, the spin down state is going to be this thing. And then what we said is that suppose that we want to find out what is the eigenstate of the spin operator, but which is pointing in some general direction n, where n is a vector which lies in the yz plane. So n is a unit vector. So the x component is 0. The y component is, say, sine of theta, and the z component is cosine of theta. So if I draw a picture, this is my y-axis, and this is my z-axis, and the direction that we are considering is some arbitrary direction in the yz plane. It makes an angle theta with the z-axis. And then what we are said is that, okay, taking such a unit vector and dotting it with our spin operator, then we basically get the spin operator in the nth direction. Now, what are the eigenstates of this operator? So let's call the eigenstates of those operator. Well, we basically we wanted the up eigenstate. The up eigenstate is going to be plus theta, and we said this is going to be a times plus z plus b plus then minus z. Okay, and then we said, okay, we want Sn acting on plus theta to be plus half plus theta, and this was an eigenvalue equation, and we solved the eigenvalue equation, and we found that A is going to be cosine of theta by 2, and B is I sine of theta by 2. And therefore, our plus theta eigenvector is cosine of theta by 2 plus z plus I sine theta by 2 minus of z. Of course, the natural question, so this is where we ended. The natural question would be to ask, what is minus theta? So we want minus theta to be orthogonal to this thing. So, you can then solve the eigenvalue equation again, but here instead of plus, you can have minus, and minus here instead of plus here. And if you do the same thing, you should get something like cosine of theta by 2 plus z minus I sine of theta by 2 minus of z. Now, we have to make sure that these states we have to verify that these states are orthonormal. They form an orthonormal basis. Let's do that. So we take plus theta, and of course this thing is by definition orthogonal to this, right? So, but it's also normalized. So we get cosine squared of theta by 2. This I, when we take the bra, becomes minus I. So minus I times plus I will give me a plus sign here. And then I will get sine square theta by 2. And this is multiplied by 1 because of the norm of this state. And this is multiplied by 1 because of the norm of this state. Thus we see this is 1. So yes, this is this is normalized. Similarly, you can show that this is also normalized. This minus sign does not change it. But is it orthogonal? So let's see. Plus of theta, and then what is plus of theta? And then minus of theta. Now plus of theta is going to be cosine of theta by 2, then plus z, and now this plus I will become minus I. And then I will have sine of theta by 2 minus of z. Okay? And then this thing will become cos of theta by 2 plus of z. And here the minus sign will remain minus sign because we are not taking the Hermitian conjugate of this. So this is this thing, right? And so now, this term, sorry about that, my kitten is meowing. This term will be orthogonal to this term, and this term will be orthogonal to this term. So you don't have to worry about those terms, but this term will multiply this term to give me cosine squared of theta by 2. This and this will give me 1. And then here I get plus minus minus, and then what do I get? I get plus, and then I get a minus sign, right? So so I will get a sine squared theta by 2. Now that doesn't look 0, right? What did I do wrong? Just 1 second.
So there's an plus I in the plus comma theta. Oh no, there
yeah,
is
but
no.
that becomes a minus sign, right? So
yeah.
Oh yeah, no, yeah. This is okay. So this is 1 minus sine squared theta by 2, and this is, so this becomes 2. Oh yeah, of course, yes. Yeah. So sorry, yeah. So this is correct. Basically, what happens is that this is 0. When is this 0? When this thing, when sine squared theta by 2 is half, right? So when this is half, it's half when theta is, what is theta going to be? When sine of theta by 2 is 1 over square root of 2. That means when theta is 90 degrees, right? Do you agree? So, so it's only, so these two states are really only orthogonal when theta is equal to 90 degrees, right? So what does this mean? What it means is that if we, like what we have found is that we have found another set of orthonormal states, which is plus of y and minus of y, okay? Because it's only when theta is 90 degrees that this state becomes this, and this state becomes theta equals to, this state becomes this, okay? All right, so this is So these two states are not going to be in general, part of an orthonormal set, but only for a specific value of theta are they going to be orthonormal. Okay. So we have found another set of orthonormal vectors, and these vectors are this and this, and of course, these vectors, if I express them in terms of my original vectors, it'll be plus of z plus I. Sorry about that. This kitten wants to go out, but there's a dog outside which might eat it, so I'm not going to let it out. Okay, does that make sense?
Yes, sir.
Questions? Sorry about the noise in the background. They will settle down. They're just hungry. Okay, any questions?
No, sir.
Okay, all right, good. So now what we want to do is we want to discuss the physics of spin, okay? And to discuss the physics of spin, okay, so one other side note is that there does exist, this vector will have an orthonormal, an orthogonal counterpart. It's just that that vector is not this vector. Okay, so you're welcome to find out what the orthonormal, the orthogonal part, counterpart of this vector is. Okay.